Uh, Hi everyone. I will be presenting latest work. I'm Dimitrios Stoidis. I work with Andrea Cavallaro, my supervisor, and I will present our latest publication, Interspeech 2021, the title Protecting Gender Identity with Disentangled Speech Representation. A bit of look on the motivation. The main motivation behind this work is that there are many privacy risks related to sharing of voice, such as speaker profiling or biased decision making. Furthermore, biometric information that is embedded in speech is not always necessary for downstream tasks, such as automatic speech recognition. And we also want to verify if gender information can be used to protect the identity of the speaker as well. So our main contribution is that we provide learnable embeddings to independently encode gender and identity attributes. We also show an improvement on the privacy utility trade-off with respect to existing state-of-the-art methods that use identity information. And we show that gender information can be used to protect the identity of the speaker as well. Therefore, we define 5 privacy settings with respect to 2 biometric attributes, namely identity and gender. So in the same scenario, the biometric attribute will remain the same as the source speaker, whereas in the random scenario, the biometric attribute will be randomly assigned. As for example, in the RI setting, in the random identity, a random identity from a speaker in the set will be chosen. Whereas in RG, for example, a random gender, male or female, will be assigned to the speech when reconstructing the voice. We also provide combined settings, such as RISG and SIRG, where one attribute is fixed and the other is randomly assigned. As, for example, SIRG, the same identity will be kept, and whereas a random gender, male or female, will be mapped onto the speech content to reconstruct the voice. So our proposed methods consist of 4 steps, and we use disentangled representation learning to protect gender and identity attributes from inference. So in the first step, we want to obtain a quantized discrete latent space containing only speech content information, and we use a vector quantization technique to achieve this. In step 2, the decoder is trained to disentangle the identity and gender embeddings from the content information. And in the next step, the task is to reconstruct voices by decoding according to the defined privacy settings in the previous slide. And finally, we validate the voices with respect to the performance on the privacy and utility. So the model architecture is a simple encoder-decoder structure where the encoder has the task to compress speech content information such that we can obtain a discrete space of content with vector quantization. And this is possible by using a nearest neighbor lookup between the embedding vectors or code words that are contained within a learned embedding space or code book and the quantized content vectors. The decoder has the task to reconstruct speech with respect to the desired privacy settings. Therefore, we add an additional get recurrent unit layer such that we can combine the identity and gender embeddings that are learned through training. And in the next step, the disentangled identity and gender embeddings are finally concatenated with quantized content such that we are able to reconstruct the speech with the privacy settings that is desired. So you can see here in the graph below the architecture, the model architecture. So first, the raw waveform signal is input into the encoder to obtain a continuous latent space Z. So if we zoom in this latent space, which is also called the discretization bottleneck, we can see that nearest neighbor mapping is applied between the continuous latent space where some regions are assigned with respect to the most similar code word E1 through EK that are contained inside in a learned code book containing then K code words. And so the index is then assigned to each region of this latent space the region of the code word, and then nearest neighbor mapping is applied again with the code words of the code book, such that we get at the end a quantized latent space containing only content information, the vector ZQ. Then this vector Z of quantized content is fed into the decoder for reconstruction, and is concatenated with the gender and identity embeddings that are learned. And through two gated recurrent layers, we're able to reconstruct speech with the desired privacy setting. So for example, here both identity and gender are used to reconstruct speech. So this would correspond to the RISG and SIRG settings, where both attributes are used. Our results show that we are able to improve upon the privacy utility trade-off with respect to existing state-of-the-art methods that use identity information in a same or random scenario. We can see that by using gender information, we are able to maintain the speech utility to a satisfactory level, and also obtain the privacy objectives, which are denoted by 50% accuracy, both in the gender recognition task and in the speaker verification task, denoted by the equal error rate. Also, we can see in the RG setting, the random gender setting that contains only gender information, that we are able to protect the identity of the speaker, as seen by the equal error rate number close to 50%, which denotes randomness in classifier being able to predict the correct gender or verify the identity of the speaker. The results here show in terms of error rates, so that we can compare both measures for gender and identity with respect to gender to error rates. So the black horizontal line denotes the privacy objective at 50% randomness. And we can see that methods that include gender information are able to achieve the privacy objective while maintaining a good level of utility of speech. And as a conclusion, we can say that we can protect the identity and gender against attribute inference by using disentangled representation of speech. And also we have shown that gender information can be used to protect the identity of the speaker. And we have shown an improvement from the privacy utility trade-off by including gender information with respect to current state-of-the-art methods that use only identity information. Thank you very much.